all the conditions in this field are more or less well suited to the growth of this plant, well, it's haphazard where the seeds land and which ones actually take. And you look at the dispersal in this field, it's basically pretty random, the dispersal of individuals in that field. Look at a group of gannets like this and the way they're arrayed in a nesting area, and you see that they're relatively evenly spaced. What's the distance between them? Well, it's about the length of their neck plus their beak. It's about how far they could reach to nip their neighbor, and they space themselves out to make themselves as comfortable as they can in the face of neighborhood competition for space, to have these nesting sites, to raise chicks, or the penguins that we've looked at in a previous example, uniformly dispersed as a result of competition or territoriality. If you go up into the hills around water, you might hear that. And that's a kingfisher full of itself. Often after they catch a fish, they'll find a person, they'll give those nice rattles. They're funny birds. They're really impressive and at the same time really comical. And they're very territorial. So those calls are meant to signal to the other individuals, this is my territory. And as a result of that type of territoriality and those types of calls, you can get uniform dispersal among the individuals. They disperse themselves along these waterways, around the shoreline, in a regular fashion as a result of some behavioral means of territorial display, or a cat marking its territory. That can lead to uniform dispersal. How about these plants in this arid area? You have a highland here. Think of these plants here. Think of this type right here. It's relatively uniformly dispersed. Why? What do you think? How can you explain it? You're an ecologist. You explain the interactions that influence the distribution and abundance of this plant. How can you explain it? So they may compete for, say, light. And yes, maybe. In this environment, I would expect light not to be a major limiting resource. So you may be correct in competition, but maybe for water or something like that in an arid landscape. If water is in short supply, they may not be able to clump because of competitive pressure. There's just not enough. Another example? Another reason? Someone's going to say water? Yeah. Anything else? Yes. Soil resources, mineral resources? Yes, so resources in general that might be in short supply. Competition by its nature has to do with resources that are finite in short supply. Any other reasons that you can think of? There's one big one in plants that's actually relatively common and is known from these sort of semi-arid areas. Space for the roots, so spatial competition. I'm still putting that into the category of resource competition because space is a resource. It's finite, it's limited, and it can get used up. Pollination? Possibly. I can't quite reason that one through. The one I'm thinking of has to do with chemicals that the individual plants release. Allelochemicals, A-L-L-E-L-O. Allelochemicals are commonly used by plants to basically repel other plants of their same kind. It's a toxin that they can use to repel other plants and keep them away, keep them at bay. And that leads to regular spacing. Allelochemicals can. Think of wolves. Wolves are dispersed in packs, right? So packs of usually related individuals dispersed across the landscape can lead to a clumped distribution. Be sensitive to scale when you are analyzing dispersal patterns, because you can look at the dispersal of individuals within a pack, or you can look at the dispersal of packs, or you can look at the dispersal of whole populations and whole regions around the whole Arctic. You need to be, your dispersal pattern for an organism can change depending on what scale you look at it. Tide pools are often a place of clumping, either because of the abiotic conditions suitable in particular pools, or the resources, or both. The mussels here might be mapping onto certain abiotic variables and conditions, where the sea stars are mapping onto the mussels that they eat. So different explanations for clumpy distributions in the two of these guys. But be sensitive to scale. Think about mushrooms like this. On this log here, how do they appear to be dispersed? If we think of these as individuals for the moment, they may all be the fruiting bodies of a single individual, but let's just think about, you haven't had botany yet, so we can treat it naively. How do they look in terms of their dispersal here on that trunk? Excuse? They look relatively uniform to me. I don't know. You'd have to quantify it. But now think about the number of dead trunks available in this little patch of forest. There may be 10 of them in a 100 by 100 square meter plot, and the mushrooms look like that on each one. At the scale of the forest plot, they're patchy because they occur in these little patches related to the rotting logs. On the log, it's uniform. It's a scalar issue. And just like ecologists are good at moving across levels, they're good at moving across scales, and you always need to think fluidly, dynamically like that in ecology, or you end up in silly arguments. Because one person's arguing for one point where they're perfectly correct, but narrowly focused. The other person has a correct argument, but also narrowly focused. And it's a silly argument because if you would take a broader focus to both of you, you would see that you're both partly correct. That happens a lot in ecology. So life in a group. Why do animals live in groups? The pros and cons of group life. Some of the ideas. Think about these fish being preyed upon by these sharks. They're in a massive school. Well, there's safety in numbers. For any individual, if an individual were to get separated from the school, they'd be toast, because off on their own, they are defenseless, really, against the sharks. But moving in the school, they're less likely to be killed than they are if they were by themselves. You see this in another type of pigeon related to a predatory bird, a bird that eats birds, like the peregrine, this goshawk. And just click this for a spectacular video of a goshawk in action. Well, here's some data from a study that showed that the number of pigeons that are in a flock is related to the distance at which these predators are spotted. The more pigeons in the flock, the more quickly and from a further distance are the predators spotted to alert the pigeons in the group about that danger. Because of communication within the group. You have many eyes in the group. You have more eyes than two in the flock. Some people call this the many eyes hypothesis for flocking behavior against predation. And you can see how the success rate of the hawk's attacks go down depending on the size of the flock of birds. You might need to huddle to thermoregulate, whereas an individual isolated bird would freeze. You can alter the abiotic conditions as a result of group living. Group foraging. Painted dogs can hunt together in the same systems that cheetahs and lions are in, but they can kill game much bigger than themselves because they do it cooperatively. Or these ants dismembering an organism much larger than themselves. A more benign case of these white pelicans, which you can see in East Bay. I was hiking with my family in just one of these reservoirs just over the Berkeley Hills here, and there was a flock of white pelicans there. It's a spectacular California bird that you can see if you go looking. And they hunt in big groups. They form these rafts where they'll herd fish basically, and then they're better able to catch them as a group, as they herd the fish together. But some of the drawbacks to group life include the transmission of pathogens. Living closely together, rubbing shoulders like that, can make it easy for pathogens to be communicated across individuals. And that can limit population size. So populations can run into these checks to their growth as a result of things like pathogen transmission or the size of the flocks themselves. This is a louse that eats the feathers of the bird, and they can be more abundant in larger flocks. So to flock or not to flock, I have listed some reasons that you can explore and think about. Good thing they're in a group, right? You wouldn't want to be by yourself in that circumstance. Let me introduce this concept. This is really important. Just a few more minutes, so hang in there for this. The principle of allocation. We'll be using this throughout the rest of the series to think about trade-offs in the way organisms exist. And we're distinguishing resources from conditions. The resources are these finite elements that organisms require, and you can think of them as food and space, things like that, and the conditions in which they grow, which can be abiotic or biotic, things like temperature, humidity, and moisture levels. Well, all organisms require a certain amount of resources to maintain themselves, to homeostatically maintain their existence. There's a basic amount of resources that need to go into maintenance if the organism is going to survive. Other ingredients of that resource, the resources that are required, go to the organism defending itself. And if you're a plant, that may mean making chemicals that herbivores have a hard time digesting, or it might mean an otter chasing away a crocodile, the energy expended in defending itself. But also to growth and to reproduction, critical ingredients in Darwinian fitness, right? All these things are supplied based on a normal set of resources for an organism. When resources are abundant, they still need to maintain themselves. But they can dedicate more of those resources to these other things. They may reproduce more, they may grow faster, they may be better able to defend themselves, and thus more likely to survive and reproduce another year when resources are flush. But when conditions are stressful, say resources are normal, but the conditions are really stressful, like it's really hot, more energy needs to go into just maintenance, basic maintenance. If it's really hot, the kangaroo might need to spend more energy seeking shelter and using water to cause evaporative cooling. That leaves less for these other aspects of the organism's life history. So this is what's meant by trade-offs in the system. This is broadly the sense in which there's no free lunch in ecology, where if something has to give when something is utilized in a different way like that. So let's think about the principle of allocation as we move through ecology. I'm going to continue here for 2 more minutes. In terms of how resources are acquired by organisms, it's not just that the more resources, the better. There's often constraints in resource acquisition. So something like the way light is captured by plants. The rate of photosynthesis doesn't just keep going up and up as light becomes more available, more intense. It plateaus. The mechanics of the photosynthetic process, the physiological tools for photosynthesis are themselves limited within a plant. It just can't keep photosynthesizing faster and faster and more and more. It plateaus. And different plants will have different shaped curves in terms of photosynthetic rate and light intensity. Some will be more efficient at low light, some will be more efficient at full sun. But all will be constrained about just how fast they can acquire resources. Same idea here, this little kangaroo rat, and you can do this if you go camping down in Mojave or somewhere like that. You can put some seed out at night and actually watch these things. They're not that shy, kangaroo rats. You can put seed out, but the more seed you put out doesn't mean the faster they're going to harvest it. They reach a limit. Their hands are pretty small. Their hands are working hard under there and they're stuffing it in their cheeks. And they can only stuff so much per unit time. We'll continue with that next time.